is going to continue with the O-minimality business that he introduced to us yesterday. So anytime.
Great, thanks. Let me just get organized here. Yeah, so yesterday, was pretty, pretty devoid of Hodge theory. So today we want to sort of see how a lot of the functions showing up in Hodge theory actually are tame with respect to this perspective of O-minimality that we were developing yesterday. So this should be pretty fun, hopefully. I'm going to warn you in advance. It takes longer to prepare slides than I had hoped. Turns out this lecture should be okay, and then the third lecture I'm just going to have to do by hand. Anyway, we'll get to that when I get to it. All right, so let's just give a quick recap of where we were yesterday. Basically, I mean, we introduced sort of the general notion of a structure as being some class of sets, or if you want, some class of functions that satisfy some properties. And then we talked about what it means for that structure to be O-minimal. As I briefly mentioned yesterday, there's really only one so far that has had very important implications in algebraic geometry, and that's this structure Rn(exp). Okay, so that's the one we're going to exclusively be working with today, which, as we saw yesterday, is O-minimal. So whenever I say definable, I'm going to mean definable within this structure. Okay, so we'll freely talk about, subsets of Rn being definable or functions being definable, and this will all mean definable with respect to Rn(exp). Okay, and just to recall, what are the sets that are definable with respect to the structure? They're all sets that are defined in terms of first order formulas involving inequalities, polynomials, real exponentials, and these over-convergent real analytic functions. Okay, so we'll get some sort of hands-on experience with this structure today. Let me just briefly recap some of the nice properties these subsets have. Any definable subset of Rn will have finitely many connected components automatically. Any definable function, real function, will be Ck except at finitely many points. Any definable subset of Rn has a finite stratification by Ck manifolds. Whenever we have a definable function between two definable sets with finite fibers, then there's a uniform bound on the size of the fibers. Okay, so most of these we won't use today. Some of them we might use, but just to keep in your head as some nice properties that these subsets will form. Okay, so let's start off with a pretty simple example, but one that's actually going to be pretty important. And let's consider the complex exponential. Okay, you should forget that as the quotient map. Just consider the complex exponential. Now, remember from this function has no hope of being definable because it's infinitely periodic. Okay. However, importantly, if we draw sort of a picture like this, so this is sort of the imaginary axis, and maybe this is 1/2 plus the imaginary axis. Importantly, if we e to the 2 pi I z looks like this explicitly in terms of its real and imaginary parts. And we know that real exponentials, this part, is definable within this structure. Cosine and sine are bad if we allow x to go through its entire, all real numbers. But if we restrict to any bounded interval, then it's restricted analytic. Okay, so this complex exponential, when restricted to any bounded vertical strip, will be definable. Okay, so that's the important point I want to make, where this V is, for instance, this V is any bounded vertical strip. Okay, and this is kind of hints at why this RNX structure ends up being so useful in algebraic geometry, because usually complex logs don't show up in algebraic geometry. It's just the complex logs on bounded angular sectors, and there's actually quite a bit of difference between the two. So let me give a Hodge theory example that is sort of in line with that, and hopefully this touches on some notions that Matt already talked about this morning. So suppose we have a variation of polarized pure integral Hodge structures over a polydisk. And let's consider the associated period map to the period domain D. Okay. Then just sort of as a recap, the period domain D is some real semi-algebraic subset of an algebraic variety parametrizing Hodge filtrations. And there's some algebraic group G floating around which acts algebraically on that flag variety. Here's the lemma. If I take any bounded vertical strip inside the upper half plane, then very similar to this exponential example we just did, the period map restricted to the nth product of these bounded vertical strips is definable. Okay, and so again, let's just be precise about what we mean by this. D is a semi-algebraic subset inside this algebraic variety, so that gives a natural notion of what it means for a subset of D to be definable. It's enough for it to be definable in this algebraic variety. And likewise here, V to the n, we're sort of identifying the upper half plane with a semi-algebraic subset of a real semi-algebraic subset of C, which we're thinking as yesterday as just R squared by taking real and imaginary parts. Okay. And no questions about the statement of this lemma, right? Okay. What's the proof? So I think Matt talked about the nilpotent orbit theorem this morning. Is that correct?
Yes. Yes.
Yes. Okay, great. Okay, so by the nilpotent orbit theorem, we know that sort of after untwisting by monodromy, this period map extends over the puncture of this polydisk, or whatever the punctures of this polydisk, as this monodromy invariant function psi. Okay. And this psi is a complex analytic function from the entire polydisk. And hence it's restricted analytic if we shrink the radius of the polydisk a little bit. Okay. So this function, this function is definable. E to the 2 pi I z from a bounded vertical strip to the punctured disk, as we just saw, is definable. So that means this whole chunk is definable. And finally, this variation of Hodge structures has quasi-unipotent monodromy. So this guy is actually, it doesn't make a difference, but we may as well, let's just assume it has unipotent monodromy, so it's easier to make this argument. If the monodromies are all unipotent, then these NIs are nilpotent, and this exponential is actually just some polynomial. This is some element of this group GC, which is polynomial in the ZIs. Okay. So this matrix is, just some algebraic function of the ZIs, and the action of GC on D check is definable because it's algebraic. So the action of this part, so we know that this chunk is definable, and the action of this on that is definable. So this whole thing is definable. Okay, so this is related to what I was saying yesterday, that the structure Rnx is like exactly what we need in order to do Hodge theory. And as you can see, we've used sort of very strongly the fact that we have real exponentials in the form of this being definable. And we've also used that we have restricted, arbitrary restricted analytic functions. And that was to get this psi to be definable. Okay, so I should say now, let me go back to what this asterisk means. You notice that during the course of this argument, I had to restrict the radius of the polydisk a little bit. So what I mean by a bounded star vertical strip is in the upper half plane, we want it sort of bounded on the sides and bounded on the bottom. So something that looks like this. So taking something that's bounded from the bottom is equivalent to shrinking the polydisk a little bit. This is what phi is equal to. Okay, so any questions about this or its proof? This is kind of an important example. It's actually surprisingly simple. Okay, so I've strictly speaking maybe used this already a little bit, but at this point we want to talk about definable manifolds, because up till now we've only talked about definable subsets of Rn, and obviously we need to relax that notion so we can talk about what it means to be definable in more exotic spaces. Although secretly, as I was also mentioning yesterday, you can often embed definable manifolds into Rn, but we don't want to do that. And there's no surprises in this definition. I mean, I'm going to write it down slightly imprecisely, but that's because you can write down the precise version and there are no subtleties, okay? The definition is, let's first define what it means to have a definable atlas on a topological space. It's just a finite atlas by definable open subsets of Rn, so meaning a finite cover equipped with charts that map to definable subsets of Rn, such that all the transition functions are definable, okay? Which makes sense because the transition functions are maps between subsets of Rn. Okay, so the most important, I mean, obviously having the charts, the transition functions being definable is important, but having the atlas be finite is also incredibly important, because you can imagine, definable sets have all these nice finiteness properties. If I don't take a finite atlas, then you could easily start destroying those finiteness properties. As you would expect, a definable manifold is then just a topological space equipped with an equivalence class of definable atlases, with the obvious notion of equivalence classes of definable atlases. Okay, so let's start giving some examples. The easiest example is complex algebraic varieties themselves. Okay, and this is a very easy example. Take a complex algebraic variety X. Okay, by definition, it's covered by finitely many affine varieties and glued by polynomial transition functions. Okay, so affine algebraic varieties are just zero sets of complex polynomials inside c to the n. And in particular, if we're just sort of viewing c to the n as r to the 2n via real and imaginary parts, they're a special kind of real algebraic subset of c to the n, and therefore they have a natural definable structure, and the transition functions are definable, and therefore the algebraic varieties have a natural structure of a I should say, since we're talking about definable manifolds, I should say smooth. Have a natural structure of a definable complex manifold. And you can convince yourself that any cover by affine varieties will give you an equivalent definable structure. That's basically because any two can be refined by a smaller one, and all the transition functions are again given by polynomials. Okay, so that's one example. I don't know why I have a second slide here. Let's give algebraic varieties a second definable atlas that's going to be useful. That's very different, but will be useful for a bunch of applications. So this is going to use the fact that any smooth algebraic variety is compactifiable. So start with a smooth complex algebraic variety. Take some log smooth algebraic compactification. Okay, so the compactification can be covered by finitely many polydisks, such that in those polydisks, the boundary looks like a union of coordinate hypersurfaces. Then by restricting to X, we get a cover by finitely many punctured polydisks. Okay. And the important point here is that this gives a natural definable atlas to X once we shrink all the polydisks potentially a little bit, right? Because our structure Rnx includes all restricted analytic functions. So obviously the transition functions for this cover are analytic. And so if I shrink all the polydisks a tiny bit, then all the transition functions are restricted analytic, okay? So this gives us a finite atlas with definable transition functions. And now if we use the sort of first example we gave of the complex exponential being definable on bounded angular sectors, we can in fact, if we like, subdivide each of these punctured polydisks into finitely many products of bounded angular sectors. And so then we get a cover, a definable atlas of X by simply connected definable open subsets. And moreover, for which the log coordinates are defined on the elements of that cover, of that atlas. So that's nice. And let me also mention that, in fact, these two definable structures are the same. And they have to be, because again, because we're working within a structure that contains all restricted analytic functions, a compact complex manifold can only has a unique structure of a definable manifold, right? Because if you have any two different manifold structures by this trick of sort of, since it's compact, you can, any atlas is refined by a finite one, and you can always shrink each set a little bit to make all the transition functions restricted analytic. So both of these two structures of a definable complex manifold that we've constructed, one coming from its algebraic structure and the other coming from its compactifiability, have to in fact be the same because it's algebraically compactifiable. And so obviously the sort of algebraic definable structure we constructed can also be constructed by taking the algebraic compactification and taking the algebraic definable structure we made there and then just restricting it. Does that make sense? Basically, maybe another way to say it is these two definable structures that we've made on X both come via restriction from X bar, and then on X bar, any two definable manifold structures have to be the same because it's compact by the argument I was giving. Okay, so this is kind of another salient point that once again, sort of the definable structures is really capturing something about asymptotics. So we have, if we have compactifiable spaces, then how to say, if you have a compact space, then there's no asymptotic. So there's really no choice in the definable structure. If you have a non-compactifiable space, which we will encounter because, you know, moduli spaces of Hodge structures are non-compactifiable, then you'll get something interesting. Okay, so let me give another example of a slightly different flavor, but kind of in a similar theme, and that is of a Riemann surface. So let's take a Riemann surface, possibly one with punctures, finite volume though. Okay, so we just got through making a definable complex manifold structure on this, coming from its algebraic structure, because any finite volume Riemann surface has a unique algebraic structure. But we can make another one using uniformization. So this Riemann surface is a quotient of the upper half plane by some action of a discrete subgroup of SL2R. Okay, and we know that we know some things. So let me so gamma inside of SL2R is discrete. Now SL2R acts on the upper half plane algebraically, right? This is just the algebraic. This is just the action by Mobius transformations, okay? And we know that we can always find a semi-algebraic fundamental set or fundamental domain even for this action. You know, they typically look something like this. Yeah, so let's call this F. There exists F, a semi-algebraic fundamental set. Okay, so now we have a semi-algebraic fundamental set for an algebraic action. That's enough to give the quotient the structure of a definable complex manifold. In fact, it's definable over the smaller structure R-alg, because we're taking a bunch of semi-algebraic sets and we're gluing them via algebraic functions, right? So, I mean, strictly speaking, in order to get an actual cover, you might want to break this fundamental set up into pieces so that they actually inject downstairs, but you can always do that. I don't know, something like this. But it's not necessary. It's sufficient to have just a semi-algebraic fundamental set such that the induced equivalence relation is semi-algebraic. Okay, so this gives us some new structure of a definable manifold on this quotient. So these two things together give quotient structure of definable manifold. Oops, sorry. Stupid. Where was it? Here we go. Of definable manifolds. Okay. Well, how does this compare to the definable manifold structure we already built on this curve? Well, perhaps not surprisingly, they're the same. How do we see that? It's entirely, again, because we have all restricted analytic functions, it's really just a statement about the cusps, okay? Because everywhere else, the definable manifold structure is just the same as the manifold structure. So, you know, both give the same complex manifold structure and therefore give the same definable structure, at least away from the cusps. And then there's some question about whether the sort of asymptotics they single out as being tame are the same near the cusps. And the answer is they are, because we know that this quotient map, for any choice of cusp, this quotient map factors through just modding out by the unipotent stabilizer of that cusp. Okay, and the quotient of that is just a punctured disk. And if we take a small enough disk around the center of that punctured disk that injects into a neighborhood of the corresponding cusp here. Okay, and the point here is that this map is just given by e to the 2 pi I z, I don't know, over L, where L is the sort of the width of this fundamental domain. And this, as we've seen, is definable, right? Because we're only looking at it on a bounded strip. And therefore, how to say, what do I want to say? Because this sort of red disk is embedding here, that means the sort of canonical coordinate here, Q, is giving the sort of compactifiable coordinate on the Riemann surface with respect to the algebraic definable structure. So what we're saying here is that the sort of algebraic definable structure is given by a coordinate which is related to the definable coordinate of this this quotient definable structure via e to the 2 pi I z over L, which is definable in Rnx. Okay, so the sort of the this is maybe intuitively obvious, but it's good to be precise about these things. Basically, what we're saying, just to summarize in words, the compactifiable coordinate for the algebraic definable structure is related by restricted analytic functions to this e to the 2 pi I z over L function in some neighborhood of the cusp, which is in turn the coordinate that is defining the definable manifold structure for the second structure that we cooked up. Okay. Does that make sense? Okay.
Sorry, can I ask a very quick question?
Yeah, please, yeah.
Is this uniformization process just a local thing of the, let's say, the manifold on the right, or does it cover, say, the full manifold?
No, this is a very global thing. Mm-hmm. Yeah, this is like the global complex uniformization. So the whole Riemann surface is the upper half plane modulo gamma.
Oh, okay, thanks. And this procedure is general. I mean, it holds for whatever Riemannian manifold we can think of.
I mean, I think you have to be a little more careful in general, right? Because, I mean, what is the uniformization you want? Just via the exponential map or something?
I don't know, I would say whatever. I mean, is this related to the transition functions that you may have to the Riemann manifold, for instance?
I mean, this is special to curves. I mean, this is related to the existence of a metric which has constant curvature. This particular uniformization. Whoops.
Oh, okay, okay.
Right, because we're explicitly. I mean, it's sort of necessary after the fact because we're writing it as a quotient of a homogeneous space by a group of isometries. Right. So something like that isn't going to in general be true. This is special to Riemann surfaces, but there are situations in which you have some similar phenomenon, and in fact, moduli spaces of Hodge structures will be an example of that, of sort of homogeneous spaces modulo discrete groups of isometries.
Oh yeah. Okay, thanks.
Mm-hmm. Yep, and we'll see a similar phenomenon. This is why I'm giving this example. Sort of this will very sort of nicely generalize to the case of moduli spaces of Hodge structures.
This is kind of true for every manifold which can be written as such a quotient, right?
Yes, yeah, right. If I mean, another way to spin this example, maybe the better way to spin this example is like if I'm taking a space let's even say that it's a semi-algebraic subset of some Rn. If I'm taking a quotient of that by some discrete group, then I can naturally build the structure of a definable manifold on the quotient by just finding a definable fundamental set for the action of that group. Okay, this is kind of a top-down, the previous examples were sort of building a definable manifold structure directly on the space downstairs. This is kind of a way of, if I can write it as a quotient, of sort of using the uniformized geometry to build a definable manifold structure. Okay, and for Riemann surfaces, the point is they're the same. They won't in general be. Okay, so here's another example that is sort of getting more towards what I was talking a bit about last time. And this is the example of flat vector bundles. So let E be a complex vector bundle with a flat connection on a smooth complex algebraic variety X. Then there are two natural definable structures on E, which I'm going to consider as a geometric space, sort of the total space of this complex vector bundle. And the two algebraic structures here are in some sense analogous to the two ones we were just discussing on a Riemann surface. Okay, so first of all, there's an algebraic definable structure on E, which is constructed as follows. Take a log smooth compactification of X, okay? And there is a canonical extension of E as a complex vector but with a flat connection to X bar as a complex vector bundle with a flat connection with log poles. This is called the Deligne extension. And it's very explicit. I mean, to build this extension, it's enough to locally specify what the analytic frame that extends to give you a frame on the compactified bundle is. And the way I build such a frame is I take flat sections V I take some polydisk neighborhood of a point in the boundary with respect to this log smooth compactification. I take some flat section in that polydisk. Now, it's going to be a multi-valued section because there will be monodromy around the boundary divisors. But the important point is the monodromy is abelian. And therefore, I can, just as I was sort of doing in the nilpotent orbit theorem, I can untwist by the monodromy. And therefore, I can make analytic sections of this bundle which have no monodromy of this form. Okay, and I declare these to be the ones which extend to E bar. And then one has to show that, on overlaps between polydisks, these two frames are giving the same structure of an analytic bundle. Whoops. So there's some content there. But that's what this extension is, and you can check yourself that these sections, the connection applied to these sections give you log poles. And so now we have a complex analytic bundle E bar on X bar with a connection with log poles. Well, just forget about the connection for the moment. We just have an analytic vector bundle on a compact now algebraic variety. And by Gaga, that means it has a unique algebraic structure. And therefore, by restricting to E, we have an algebraic structure on E. And in fact, one can be a little more precise about the uniqueness of this algebraic structure. It's the unique algebraic structure for which the connection has regular singularities. Okay, but that's not going to matter so much for us. As soon as E has an algebraic structure, as we've seen, I mean, if that means the sort of geometric space has the structure in algebraic variety, and therefore it has a definable structure by covering by affine algebraic varieties. Okay. So that's the algebraic definable structure. Even more simply, it has a flat algebraic structure. A flat definable manifold structure. And this is very easy. Take a simply connected definable cover UI of X. I should have said of X. Okay. And trivialize this flat bundle via flat sections. Should have said that too, via flat sections. Right? You know, I can always this flat connection can always be solved over simply. I mean, the only obstruction to solving it is monodromy, and you know, therefore, over any simply connected open, I can trivialize it by flat sections. And now let's just observe that the transition functions between, you know, these various trivializations are constant on the second factor, because these trivializations are given by flat sections. And so, you know, the transition functions between flat sections here and flat sections here are just, you know, matrices with constant entries. So the transition functions are constant on the second factor, and we already know they're definable on the first factor. And therefore, these transition functions are definable. Okay, so we glue it up, and this gives us a definable complex manifold structure. Okay, so if you want to think about the difference between these two definable structures, sort of tautologically, they're sort of determined by what local sections are definable with respect to each of them, and obviously the local sections which are definable in the algebraic definable manifold structure are the algebraic sections, and the flat ones are the ones that are definable with respect to the flat definable manifold structure. Okay, and these could in general be very different, because, you know, this construction of an algebraic structure, you know, these algebraic sections may be very different from the flat ones. And in general, they'll be sort of transcendently related to them. However, there's an important set of cases in which they are the same. Okay, and so this is important enough to be a theorem. And here's the precise condition. Suppose the monodromy of this flat vector bundle at infinity has norm 1 eigenvalues. Then the algebraic and flat, oops, I did not finish this, flat definable manifold structures are equivalent. Copy this, post it on subsequent slides. Okay, so what's the proof? Well, this is just sort of rehashing what I was already said. I mean, there's two kinds of coordinates on this total space of this vector bundle. There's the coordinates coming from the base, which is the same for both definable structures, and then there's the coordinates for the fibers that we're including. And in the algebraic structure, in the algebraic definable structure, those additional definable coordinates are obtained by taking coefficients with respect to an algebraic frame, and the additional definable coordinates for the flat definable structure are obtained by taking coefficients with respect to a flat frame. So to prove this theorem, we just have to show that the change of basis matrix from an algebraic frame to a flat frame is definable, right? Because then, re-expressing, then we can definably express the coordinates, the definable coordinates for the algebraic structure in terms of those for the flat structure. And this just explicitly comes from the construction from the formula I gave you for this Deligne extension. Okay, we just have to write it down. Sort of, if we take, we know that this canonical extension is locally given by a frame of the form, untwisting the monodromy of flat sections. Okay, so on the one hand, the algebraic frame is defined as being the one which analytifies to this analytic structure. Okay, so that what that means concretely is any algebraic frame is related by a change of basis matrix consisting of restricted analytic functions to this frame, because they both give the same analytic structure. And on the other hand, explicitly, we know the change of basis, excuse me, matrix between the flat frame and this frame, because it's just given by this exponential. Okay. And this exponential, if all the nks have imaginary eigenvalues, is definable. Because once again, we're only looking at this on bounded angular sectors. And so the only issue is as long as the nks have imaginary eigenvalues, we're not kind of rotating, we're sending a bounded vertical strip to a bounded vertical strip. We're not sort of rotating it. It might be a little complicated to see, but it's enough to just think of sort of an exponential of a single, not of a matrix, but of a diagonal matrix, right? If you take e to the okay, let me unwrap that. So how do we actually take this? Let me expand on this argument. How do we actually take this complex exponential? Well, these nks all commute, and we can take their Jordan decompositions for all of them. And just as before, the sort of nilpotent part just gives us polynomials when we exponentiate. So that part doesn't matter. So it really is just the diagonal part that matters. And for the diagonal part, this is going to just look like, q k to the q is equal to e to the 2 pi I z, then this is just going to equal to e to the minus z nk. Okay, so as long as nk is did I do that right? I might have screwed up. Sorry, let me just think about this for a second. I think I always get confused about whether the nks are the residues, or I think here I think the condition on the eigenvalues being norm 1 translates to these being real. So then this is definable, because again, we sort of write down what it is in terms of its real imaginary parts. We get some exponentials, we get some signs. If n had an imaginary part, then the sort of the unbounded part of this vertical strip would be absorbed. We would see it in the sine or cosine factor, and that would be a problem. Okay, so as long as that doesn't happen, then we're okay. I think that's right. Well, it's either real or one of the two, but this is the right condition. Okay, so this applies to something that we in particular care about, namely period integrals and families of algebraic varieties. And that's as follows. So let's take a smooth projective family, x over y. Then, as we know, the sort of cohomologies of the fibers assemble into a flat vector bundle via the Gauss-Manin connection, right? Because topologically, a smooth projective family is locally trivial. The topology is not changing. And we can be pretty concrete, actually, about what this kind of nebulous algebraic structure that we defined on this flat vector bundle is. it's just given by algebraic de Rham cohomology, which, you know, if you've seen before, great. You know what I'm talking about. If you haven't, then it doesn't really matter so much. But the sort of important point is that we can think of classes, or rather algebraic sections of this flat vector bundle with respect to that algebraic structure as being given by the classes of relatively closed K-forms, algebraic K-forms. Okay. On the other hand, the flat structure is much easier to understand. Taking coordinates with respect to a flat frame is just the same as integrating along a topological K-cycle in a fiber, and those you know, topological cycles can be transported to nearby fibers via the connection. So the change of basis matrix explicitly sort of between the flat frame and the algebraic frame is given by the integrals of these algebraic forms over these topological cycles considered as a function, okay? And the corollary to this theorem is that these are all definable functions. And what's the proof? The proof is that this flat vector bundle, this sort of the flat vector bundle, you know, given by the these cohomologies. I'll just say, well, let me just write it like this. Let's say like X over Y has quasi-unipotent monodromy. This is an important theorem in the theory of pure polarized integral variations of Hodge structures. What does quasi-unipotent mean? Quasi-unipotent means that all the eigenvalues of the monodromy at infinity are roots of unity. In particular, they're norm 1. So they satisfy the hypothesis of this, this theorem. Okay. So all period integrals, you know, are definable, appropriately interpreted. And the only way to actually make sense of that is I take some relatively closed algebraic K-form in the total space of my family, and I integrate it along some topological cycle that gives me a multi-valued function because the topological cycle has some monodromy. So if I take some branch of that multi-valued function over a simply connected definable subset of Y, then I get a definable function. Okay, so now let's come back to period spaces, which I alluded to before. Okay, and hopefully we've seen enough of this this morning so that I don't have to recall most of these notions. So if D is a period domain of pure polarized integral Hodge structures on some fixed lattice with some quadratic form, then as in our Riemann surface example, if I want to put a definable structure on this quotient, okay, so this is by the Z points of this algebraic group that we were referring to before. I mean, concretely, let me just say that this complex group that's this algebraic group that's floating around is just sort of the automorphisms of V that respect this quadratic form Q. So this GZ group is just the integral automorphisms of VZ that preserve that form. So in other words, you know, in the odd weight case, it's the symplectic group. In the even weight case, it's the orthogonal group. So to put a definable structure on this quotient, we just need to find a semi-algebraic fundamental set for the action of this group, okay? And I'm not saying that there's only one possible definable structure on this quotient. In fact, that's not true. There are many. There will be, not all choices of a semi-algebraic fundamental set will give compatible definable manifold structures. So we want to find one that is particularly natural. And this is done via reduction theory, okay, which I definitely am not going to get into. But it turns out, you know, there is already a satisfactory answer to the question of, you know, what is a natural semi-algebraic fundamental set for the action of this integral group on D. How to find such a whatever. What is a natural notion of a semi-algebraic fundamental set? And I'll sort of, this works more generally, but in this particular case, it has a nice interpretation in terms of the Hodge form. So we can very explicitly say what this fundamental domain is going to be. So basically we do the following. We fix some basis of Vz and some constant A, which is greater than 0. And we want to consider all Hodge structures for which the Hodge form, which I don't know if we've seen, but remember the Hodge form is related to the polarization form, the natural Hermitian form you get from the polarization form by sort of changing signs depending on whether, you know, which Hodge decomposition group you're in. And the sort of point of this Hodge form is that it's positive definite, okay? So if for a fixed basis, fixed constant A, if we look at all Hodge structures for which this Hodge form is reduced, then we will get I claim that we'll get a semi-algebraic fundamental domain. Okay, and let me just write down what I mean by it being A reduced. Well, it means the following three things. Okay, these conditions. So, you know, what I mean by this is we take this Hodge form, we get a matrix Hij by just evaluating this Hodge form on these vectors. Okay, so we get some matrix. And I first of all want this sort of strong version of Cauchy-Schwarz with respect to this constant A, meaning, you know, usual Cauchy-Schwarz tells you that every off-diagonal term is bounded by the sort of geometric mean of the two corresponding diagonal entries. And here I want to say that up to a constant, it's actually less than both diagonal entries. So it's less than the min of them. So that's this. There's some sort of volume normalization. In other words, I want the product of the diagonal entries to be you know, roughly bounded by the determinant. And I want the, up to this constant A, I want the vectors to be ordered by increasing size. Okay, so if you're not familiar with reduction theory, let me just vaguely say that what this is, the idea of reducing, finding a reduced basis for a quadratic form is roughly the following. I want to somehow, obviously there's not going to be some canonical base, given a quadratic form, there's never going to be a canonical basis. I want to nail down some kind of properties that the quadratic form might have with respect to a basis that'll sort of give me some reasonable set. And I can do the following, like I can, given a quadratic form on some lattice, I can find the vector with the smallest norm, take that as my first basis vector. And then I can find the vector with the next smallest norm that is outside of the span of that first vector, and take that as my second vector, and then so on and so forth. So these axioms are essentially characterizing that procedure. It's like you sort of take successive sort of minimal length vectors, okay? And you can imagine that that kind of basis is somewhat canonical. It's not exactly. Anyway, the point is, if I kind of turn that on its head and look at fix a basis and look at Hodge structures for which the Hodge form is reduced with respect to that basis, that gives me some subset of Hodge structures, which I am claiming is in fact a semi-algebraic fundamental set for the action of GZ. Okay, it's obviously semi-algebraic. So it's really just it being a fundamental set. So I'm not even going to try to prove this, but I will work it out in the case of the modular curve, so you can just kind of see what's going on here. So the modular curve is the example of Hodge structures that look like the H1 of an elliptic curve, and in this case, yeah.
Can I ask a quick question about your previous slide?
Yeah, sure.
Maybe I have missed something, but is your domain defined through these A reduced basis? Namely, when you can find an A reduced basis, this is your domain.
I want to fix a basis, and I want to look at those Hodge structures within D for which the Hodge form is reduced with respect to that basis.
Okay, is it always possible to find such a basis?
Like for any Hodge structure?
Yeah.
Well, if you also allow your constant to grow, then yes. If you take some fixed constant A and ask that question, no, I don't think necessarily.
Oh, okay. Okay.
Yeah, you might have to take your constant to be big, and you'll this will become more concrete when we do it for the upper half plane.
Thanks.
Yeah, sure. Okay, so for let's take D to be the upper half plane. I'll draw it like this. Here's the upper half plane. Okay, so for a point Z in the upper half plane, maybe I'll leave this as an exercise. You can compute the Hodge form. And you'll get this, take the standard, or how to say it? Let me back up a little bit. Okay, to a point Z in the upper half plane, we're taking the lattice VZ, which is generated by two vectors E and F. And let's say the quadratic form is the usual symplectic form, okay? And the Hodge structure corresponding to a point Z is the one for which the 1, 0 part is generated by Z1 with respect to this basis EF, okay? There's no reason for me to suddenly write it like that. Let's say ZE plus F, okay? So if you work out what the Hodge form is with respect to this EF basis, you'll get that it is this. Okay, where Z is X plus IY. Okay, so let's look at these conditions. So we have this strong Cauchy-Schwarz. So we should have that norm of xy over y is less than or equal to some constant times 1 over y. Okay, so that condition is clearly giving us that the absolute value of x is bounded. So that's putting us in some vertical strip. So that was half of this strong Cauchy-Schwarz. The other half is this one, less than a times this. This one's a little complicated, so I'll come back to that in a second. What else? This volume condition is saying that this product, which is this, is less than or equal to a times the determinant. The determinant is 1. So it's just, this is bounded by A. And this is just 1 plus x squared over y squared. So really what we're saying is that x squared over y squared is bounded. So that's just saying that the slope of our point is bounded from below. So this region sort of looks like one like this. So it's on the this side of this blue part. And finally, this last condition, the ordering condition, tells us that, let me put this in, I don't know, orange. This ordering condition tells us that 1 over y is less than or equal to norm z squared over y times some constant, which is just telling us that norm z squared is bigger than or equal to 1 over a. So in other words, we're like outside of some circle like this, okay? So it turns out that this condition, you know, implies this one, you know, possibly changing the constant a, so we can basically ignore it. So the answer is that the sort of the locus of Hodge structures, which are reduced with, you know, a reduced with respect to this basis, is like this set, which is very similar to the usual fundamental domain for SL2Z acting on the upper half plane. You know, by comparison, the usual fundamental domain is this one. Okay, and in fact, these two are like comparable. Okay, so that's why this is giving the, you know, the same, how to say it, the same definable structure. Okay. By, you know, by comparable, I mean, I literally just mean that, you know, whatever, this one, they're both clearly semi-algebraic, and they're both fundamental sets because each one is covered by finally many translates of the other. Okay, so I'm probably, it's probably been about an hour now, right? This is a good place to stop, actually. So let's stop here, then we'll pick up and we'll finish with this discussion, and then talk about some more advanced stuff.
Okay, thank you.
For comments?
Can you say something? So you have this this characterization of bundles, right? And then you say you find exactly this situation in the Hodge theory context, right?
Yes.
Mm-hmm. So can you? Is there something else which we could say about what goes wrong if this doesn't happen? So it's like, why is this a problem that these two structures do not agree? These two definable structures.
Well, it's not necessarily a problem, but it does mean that the sort of how to say it. I mean, it's not a problem in the sense that you know there are certain bundles for which those two definable structures are different. It's just that often, you know, when working in Hodge theory, it's nice to be able to go back and forth between the sort of flat and the sort of algebraic perspective. And obviously, if the, you know, if they're definably related, then sort of if I'm interested in sort of definable constructions, then that's okay. If they're not, then I'm going to exit sort of definable world as soon as I try to compare these two structures. Does that make sense? So it's not
so there's no, you say that you don't see a fundamental reason why they have to agree, rather other than applications.
Yeah, I mean, I can do an example for you if you'd like, but they're definitely not the same if that condition is not satisfied. It's not that, you know, we can't prove it or something. It's just that they aren't. These two definable structures are just not different, are not the same. But maybe here's maybe an answer to maybe here's an answer to the question of sort of why is it useful to be able to go back and forth between the two.
Yeah, yeah.
And we'll see more of this in the second half. But for instance, it follows. So remember, we had from yesterday this sort of definable Chow theorem, which says that if you have a closed complex analytic, you know, subvariety whose underlying set is definable, then it's algebraic. Okay. So because, you know, we deduce this corollary that periods are definable functions, and therefore we have the following fact, which is definitely not obvious, like if you have some moduli space of varieties, like, I don't know, take some moduli space of like Calabi-Yau manifolds, if you like. Suppose you have some subvariety of that space of Calabi-Yaus, which is cut out by, you know, algebraic relations on periods. Okay, you know, I can give you some kind of stupid examples where you can do that. But suppose you had some closed complex analytic subvariety of, you know, those Calabi-Yaus, which, you know, had some relation between their periods. You could then conclude from that definable Chow theorem that this is an algebraic subvariety because of the fact that those periods are definable functions. Okay, and you wouldn't, because you have some complex analytic subvariety, which is sort of locally cut out by definable functions, and therefore the underlying set is sort of definable. So you wouldn't be able to do that if you couldn't go back and forth between the sort of flat definable structure and the algebraic definable structure. Does that make sense?
Yeah, it makes sense, but it's again in the Hodge theory world somehow. So it's a. It would be interesting. It would yeah. Anyway, this is maybe too specific. Yeah.
No, I'm not trying to tell you that there's some reason that you know, there can only be this kind of useful comparison in this case where this norm one eigenvalue thing is satisfied. I mean, that just
so let me state it differently. So if they are the same, are we automatically in the Hodge theory world?
No.
Because there's some more structure, right, coming from the Hodge theory.
Yeah, there's definitely a lot more. I mean, this condition for the two structures being the same is just about the flat vector bundle. So there's no Hodge filtration floating around. There's, you know, it's purely about the monodromy. It's purely about the regular differential equation.
But it's already quite a lot, right, when it comes to Hodge.
Yeah, no, that's true.
Okay, thanks.
But also the condition, I mean, it is closer, I suppose it's closer to being a complex variation of Hodge structure. I mean, the condition that the local monodromy be norm one eigenvalues is pretty different from the monodromy being quasi-unipotent, right? Because you can, you know, there's lots of norm one, you know, complex numbers that aren't roots of unity. So it also doesn't see the integral structure at all.
Okay, thanks. Yeah, makes sense.
Anyway, sure.
Maybe some of the online participants have questions or comments. If not, well, we thank Ben again, and we make a break.